So welcome all to this very unique workshop of PSO and evolutionary algorithm. It was put together in a very non-traditional way. So typically this is the IMS that was created in 2000, July 1. And initially the funding was coming from NUS and the Ministry of Education. But after a few years later, now it's basically self-funded by NUS, and they sent out a call for proposal, which actually happens just a week or 10 days ago. Anyone can propose a workshop like this, or a longer period, either 2-3 months as well. And if it gets funded, after review by scientific panel, bring people from overseas and come here to discuss mathematical-based projects or research that you want to work on. So if you have ideas and something has to do with mathematics, because this is the Institute of Mathematical Sciences, I encourage you to put in an application and then hear the results. So typically it's funded 2 years from the date of review, right? Okay, so with that, we have a total of 8 speakers in this workshop. So usually it's longer, but this is just 2 days to roughly gauge interest, and maybe if there's enough mathematical interest, this might lead to a longer workshop later on. So there are 91 or 95 people who have signed up to participate in this workshop, which is actually a very good feedback in terms of interest from the community. So I want to thank the speakers in particular for contributing their time to come and share with us their very unique experience. So the reason why I co-organized this along with Casey Han is that I'm in biostatistics and statistics since 1990. I've done my PhD in statistics and doing optimizations. And I never ever heard of such thing until about 4 or 5 years ago. And since then, I never looked back at the algorithms that we use in statistics. So I think these things are very magical and interesting and very easy to implement, and it really seems to work well. So I'm trying to get people in statistics in particular and mathematics to look at these algorithms and try out, explore for themselves. And it's really magical. So I hope at the end of this workshop you go away with that feeling and you are more motivated to use them, and actually widely available on everywhere, just like Google. Yeah, a lot of literature, very overwhelming, but as you can see, if you don't look at for 20 years, I wasn't aware of such a thing going on. Okay, so before I call the first speaker, there's some IMS house rules I read to you. There's no food or drinks allowed in this auditorium. Speakers, please copy your presentation slides onto the PC before the start of the talk. And all speakers put on a microphone. And then NUS is a smoke-free campus. And after the first talk, there will be a photo taking session, which happens here. And then after that, followed by tea break. And then there's a lunch reception today. And tomorrow there is also lunch available at the business school, cafe, Paddy, what is the name? It's Parankan food, it's buffet, and it's I think $22. It's going to be self-pay. You can choose to go there together or not. And after that, you just pay by yourself over there. The buffet is quite nice. If you haven't tried that, you may want to try that. So there's a sign-up sheet. If there are more people, then we need to reserve tables so that we can sit together for tomorrow. Okay, so without further ado, let me call upon the first speaker, who is Professor Suganthan, who is the editor-in-chief of so Swamp Intelligence and all this stuff is very interesting. There are actually a couple of journals that are devoted to such topic. If you haven't heard of it, you'll be very amazed how widely used they are. And it's from
Nanyang.
NTU. Okay, so he's going to give us tutorial. Very generous of him to do that. Appreciate it. So he's going to give us an overview, and then after that, you'll hear from speakers with specific applications of such algorithms to solve real problems. So I'm the only one who's not an engineer or computer scientist in the speakers. So they are clearly dealing with a very complex, interesting problem. And hopefully, after the workshop, you'll be convinced how great these algorithms are. So, thank you.
Thanks, Prof. Wong Wenki, for the introduction, and I thank the organizers for inviting me. So I just finished putting up these slides last night only. So I haven't done this presentation before, the introduction to nature-inspired metaheuristics. So it's first time I am putting all these things together. So I collected some slides from Dr. Suganthan Das. He is editing the Swarm and Evolutionary Computation journal with me under Elsevier. And also one of my recent PhD students, Kai Chao Gao. So we will look at some of these algorithms. Nature-inspired, you can usually divide them into two categories. One is the evolutionary type, other one is the swarm or cultural types. So the swarm ones are becoming more popular than the evolutionary types. But my experience has been that the evolutionary types are better for problem solving, but swarm types are more attractive to people to give a story about one species or one particular animal or whatever, or bird or whatever. You can give a story and then come up with some equation. So people are attracted by that as well. If you look at the names, there are maybe 50 or hundreds of names for the algorithms now. So there are far too many new algorithms proposed. So in a way, that is not a good sign. Before I go into the talks, a couple of publicity slides. So some of my algorithms are available from my home page. So you can get some software and all those things as well related to our works mostly. And then there's an IEEE conference in India, Bangalore. This on all these methods, computational intelligence. So the topics are all computational intelligence, including neural nets, fuzzy and swarm, evolutionary, all of them are included with all the applications from any area. And also there's a multi-criterion optimization going to be in USA. I forgot to put the place. I got the email only yesterday. When I put it, I forgot to mention the name, place. It is going to be Michigan State University, organized by Kalyan Moideb. So that is. I also do work in randomization-based neural networks. So I have some resources under that category also. So you can look at them as well. This is the journal Wenki just mentioned. So we established this in about 2011, and we have been running it since then. So it has a reasonable impact factor over 2 years and 5 years as well. So you could consider submitting your works to this journal as well. So I give you a very brief general introduction to optimization, constraints, and all those things. I am not too sure how many of you are very much familiar with all these things. How many of you have all the background information, knowledge about these methods? How many do you have? How many don't have much about? So it's a mixed population anyway. Some of you don't know much about it. Some of you have some idea. So I will tell you something about the general optimization and so on, and then we'll move on to the algorithms. The algorithms, I am picking a few of them. Some of them I am familiar with. Other one, just I got the slides from Dr. Das. So there are two reasons for putting these names inside. One thing is I have been working with them, so I have the slides. And the other things I am putting in because I got the slides from Dr. Das and Dr. Gao Gai Chao. but there are far too many names to mention anyway. So I will be mentioning about 20, 25 names, but the names are more like 50 or 100 like. So the global optimization, you are basically looking for one good solution. Your optimization problem can be either maximization or minimization. But in evolutionary computation, swarm computation, we talk about fitness. So if you are looking at minimization, if the objective value goes down, your fitness is going up. But if you are doing maximization, when your function value is going up, your fitness is going up. So we talk about fitness values in evolutionary algorithms. But when you go to swarm algorithm, what they represent is really diverse. So if you talk about honeybees, they looked about the nectar. So higher the nectar you find at one location, it is better. So for them it's different. And for ant colony optimization, it is pheromone levels or something like that. Pheromones that they lay along the paths. So for swarm algorithms, what is better is going to be different. But in evolutionary terms, we call as fitness. So the fitness word is now commonly used in swarm as well. So, and also, okay, maybe I tell about other things later on. So there are so many different types of optimization problem, but this global optimization is most commonly looked at. Whenever a new algorithm is proposed, researchers evaluate them on single objective global optimization. So this is basically the basic one for you to start with. And also when you do optimization, the resources are limited. That is what we usually say. Resources means the computation time. Any optimization problem you have to solve within a finite time. You cannot have infinite time. Like simulated annealing talks about global convergence with infinite time. So in practical situations, you cannot talk like that as well. So that is why we mention limited resources and within the number of trials. Trial is basically the objective function evaluation or function evaluations. So this is one definition. So our objective is to find for the single objective optimization, global optimization, your objective is to find the optimal solution. Usually the functional form is given to you, but the swarm algorithms and evolutionary algorithms, they don't make any assumption about the functional form for your objective evaluation. So your objective evaluation, you don't really need an explicit function. It can be obtained by experiments, by taking surveys and all those things. So you can use any method to identify or compute the quality of the solution. So in the swarm and evolutionary methods, when a potential solution is given to you, you should be able to evaluate the goodness of it, how good the solution is. So that is what you need to apply these methods. So you don't need anything else. So when a valid solution is given to you or potential solution is given to you, you should be able to compute how good the solution is. So when you are given two solutions, usually you should be able to compare them. Okay, this one is better, this one is worse, and things like that. So this is what you need to apply these methods. So very basic information is needed for you to apply these methods. So you can have multidimensional, and the decision variables can be real, integer, binary, and all those things. So can be mixed as well. You can have mixed decision variables. All of them are allowed here. And you can have bound constraints. So these are known as the bound constraints or box constraints. Basically, they define upper lower limits for each decision variable. So this is usually required. And then these ones are usually the general constraints. So we are putting together inequality, equality constraints together. So you can have equality constraints as well, inequality constraints also you can have. And these are general functional forms. So briefly, I will mention some of the optimization classes that people are studying under the evolutionary swarm methods. When do you want to use meta-heuristic approaches? So this is also I will look at later on. I will mention when to use meta-heuristics, and the simple answer is that if you cannot solve a particular problem using traditional methods, only if you cannot solve, then you have to look at these methods. If you have a deterministic method that can solve a problem satisfactorily within finite time, then you should go for the traditional ones. Okay, traditional methods you should look at first. But the problem is these two communities are going separately, so we don't usually look at the traditional optimization field and see how they are advancing. So we are sort of out of touch anyway a little bit. But if you have a real world problem to solve, you should first look at the traditional methods, and if they cannot work, then you should come to this one. So sometimes I tell application researchers that you can find the best traditional method, you apply it, and then you come to this swarm and evolutionary methods and find a good method and apply it, and then look at the solutions. Then you can decide which way to go. So usually that is another approach. And also the traditional people who have been using the traditional optimization methods, they are reluctant to use swarm and evolutionary algorithms. So I try to encourage them. You use your traditional method, you have one solution, then you apply our methods, and then you have another solution. So you can compare both of them and select which one is better. But some traditional researchers, they don't like this idea as well. They want to stick with their own methods, the traditional ones, so they want to ignore them anyway. So type of solutions, when you are given a potential solution to an optimization problem, we call them candidate solutions. So when you are given a candidate solution, this solution can be a feasible one. An optimal solution is a feasible one, as well as it gives you the best possible fitness values, so objective values. So here, most of the time I am looking at single objective numerical optimization. So the context is most of the time single objective numerical optimization. Neo-optimal solution, this is what usually we look for in swarm and evolutionary algorithm methods, because these methods do not make use of gradient differential information. So there's no first order differentiation, second order differentiation. So if you ask whether these methods can give you the exact global optimum, it's difficult for these methods because these methods don't make use of the gradient information, first differentiation, second differentiation. So it is in a way unfair to expect that these methods are going to give you the global optimum defined by your differentials, because these methods don't make use of them. So if you want to expect that kind of thing, then you may have to go for numerical differentiation and things like that with these methods to show those things. So you also have continuous combinatorial optimization. The one I work mainly with is continuous optimization. You also have combinatorial cases. So you may be familiar with them as well to some extent. So in my opinion, the swarm and evolutionary algorithms are more suited for continuous optimization than combinatorial. So my experience is for combinatorial optimization, the swarm and evolutionary algorithms are not so effective if you just apply them. When you solve combinatorial problem, what is more effective is the hybridization. The swarm and evolutionary algorithms, they are capable of doing global search, but then you need the local search part to come in to solve these combinatorial problems. So without local search, these evolutionary algorithms, swarm algorithms are not so good for solving combinatorial problems. So maybe I skip some of the slides since I have quite a bit of slides. So this is definition of combinatorial optimization. And by the way, combinatorial optimization problems, why they are difficult is that the the fitness landscape or objective landscape is not very smooth in the combinatorial cases. Even if you look at this traveling salesman problem, for example, you go around a circle, you make one wrong connection, you switch across the diagonal. The global solution is only one switch apart, swap apart, but the fitness values are totally different compared to the global solution and this neo-optimal solution. That kind of situation may not happen in the real parameter optimization, real variable optimization. You may not have this problem. So the swarm evolution algorithms can do well. So in general, nature-inspired metaheuristics are not effective for solving combinatorial problems alone. So if you apply these metaheuristics alone, they won't be so good. Heuristics can be effective, but if you hybridize them, they will be actually very good. So if you hybridize them, that would give you good solutions. So constraints, when you solve a real world problem, usually there will be some constraints. Some of them are bounds constraints, some of them are functional forms. In recent time, constraints may be formulated as objective as well, and they can be treated as objective and solved by these algorithms. So this is a case where I explain the implicit constraints and explicit constraints. Some constraints can be explicitly specified where you visit only one city at a time. It's more like an implicit constraint. So this is where I list all these optimization problems we have been studying. So you have combinatorial continuous bound constraints problem for the continuous case. Most of the time I will be talking about continuous anyway. Bound constraints, this is with general constraints, single objective, multi-objective, static, dynamic. That means the objective doesn't change with time. Here the objective or the decision variables or the problem situation may be changing with time, here dynamic case. Expensive problems, usually we are talking about objective evaluation. When a particular solution is given to you, evaluating its quality, how good the solution is, it can take very long time. So in some chemical engineering processes or some civil engineering problems where you may have to employ, for example, finite element methods and things like that, then the evaluation is very costly. So you have expensive. Large scale is looking at the decision variables or number of objectives, too many objectives to work with or too many decision variables to work with. You have large scale. With without noise. Multimodal problems are where you try to find multiple solutions for even a single objective problem. And this is useful if your objective, the fitness landscape or the objective function has sort of sinusoidal shape. That means you may have many good solutions distributed in the decision variable space. So you can try to identify many of them and then select the best one for you. And why there are so many papers in this area? The reason is you can mix and match them. You can take, for example, continuous problem and then introduce constraint and then go for multi-objective and take dynamic. So now you see how many problem cases you can create. So you can have very many combinations here. Large combination of problem cases, and researchers are studying each one separately and writing papers. So that is why there are a lot of papers here. But one observation is that when you combine many of these characteristics, you are in a disadvantageous state or advantageous situation. Advantageous situation is that not many people are working in this combination. When you combine 4 or 5 features from there may not be many people working in that particular combination. So when you do the combination, you are actually asking for intersections. Intersection. When you put many intersections, the community is very small. So the advantage is when you write a paper, very likely no one has written it. So your paper may be accepted. But the bad thing is after acceptance, there may not be many people to cite your work. So you have an advantage and disadvantage with these things. So usually this is the bound constraint continuous. This one is the most crowded, I think, still. And then now the multi-objective is also becoming crowded as well. So my suggestion is that you should go into these crowded areas and do good quality work, so others will look at your work and cite. So that may be the easier strategy. So another strategy is to create your own area. That is a little bit of hard work, I think, like the extreme learning machine, where you create your own area. And then here I will mention a couple of names later on, provided I have time to go there, where they came up with, one person came up with about 10, 20 algorithms. Like. So those people are also noted anyway, so they also get high citations. Even though the methods sometimes don't perform as good as these methods, some of them I am talking about. So the deterministic search techniques, these are usually considered traditional one. And then the stochastic methods, this is what we are looking at anyway. So our search methods are usually stochastic type. And when do you want to use swarm and evolutionary algorithms type? So it has to be over here. So when you have all these difficult characteristics, multimodal, maybe not easy to differentiate, so many local solutions, very large number of local solutions, and when you put all these difficult properties, then the problem would be more suitable for swarm and evolutionary algorithms. So yeah, that is what I mentioned anyway. So this is what in this slide. So these are the terms we commonly use with swarm and evolutionary algorithms. The search solution, we work in the swarm and evolutionary algorithms, we work with population of solutions. So a solution is possibly a candidate solution that is feasible for that particular problem. And usually we work with a population of solutions. And the neighborhood terminology is very important. Neighborhood can come from the decision variable space for the single objective, but for multi-objective, neighborhood can come from the objective space also when you have multiple objectives to work with. So move, this is usually used with these swarm algorithms where the swarm population is moving from one point to another point, so you use the word move. And the evaluation is also commonly used. This is for you to evaluate the quality of a solution that can include the constraint function as well. So a couple of slides on metaheuristics, and then we will look at some of these methods. I may not have time to look at all of them, but anyway the slides are there for you, and then I give you some listing of methods, and also I give you some researchers who came up with many new names, Grey Wolf and all those things. So I copied some of these points from this particular web page as well. So heuristic is based on rule of thumb anyway. So when you talk about heuristics, you are looking at all these properties. You don't want to make use of the rigorous mathematical methods which may require lots of time to solve this problem. So how can you find a solution fast? So then you go for these heuristics, rule of thumbs. And the word meta stands for beyond. So beyond means you are looking at evolutionary concepts or swarm concepts, and you are combining with these rules to come up with these swarm and evolutionary methods. So as I mentioned to you, this metaheuristics method, usually they don't make any assumptions. So the only requirement is that when you are given two solutions, two candidate solutions for your problem, you should be able to say which one is possibly better, which one is worse, and so on. That is what you require. Okay, that is the minimum you require to apply swarm evolutionary algorithms. So this is the statement I copied from the Wikipedia page. So this is how they introduce swarm and evolutionary algorithms. Many metaheuristic methods have been published with claims of novelty and practical efficacy. While the field also features high quality research, unfortunately many of these publications have been of poor quality, vagueness, lack of conceptual evaluation, poor experimental simulation evaluations, ignorance of previous literature, that is very common as well. And nowadays, nowadays you cannot blame even a genuine author, because the literature has hundreds of names. So even a genuine researcher, if the researcher wants to summarize all these methods, I think the person may need 10 or 20 pages, I think, to talk about all these methods. So, nowadays you cannot also blame the authors for this problem, that ignorance of literature. So this is also the point I mentioned. If you wish to be known as a father of a particular invention, so nature-inspired metaheuristic is the right field for you. So if you want to propose an algorithm under your name, I propose this algorithm. But things are becoming difficult. When you see the analogies people are taking nowadays, it's becoming difficult. So when to use metaheuristics? The traditional methods with rigorous proofs and analysis can't work. I mentioned to you earlier as well. And this is also, I mentioned, this traditional optimization field and swarm and evolutionary computation field, they have diverged. I don't think you can find an expert, one person who is expert in this one and that one. So there is not much cross-checking nowadays, so we just evolve separately. And also some researchers, some reviewers, the reviewers some 10-20 years ago asked for proofs and convergence. Why I say 10-20 years ago is that in the early stage of swarm and evolutionary computation research, the community is small. So when you submit a paper, this paper can go to traditional mathematics-oriented optimization people. So when it goes to them, they will immediately ask about convergence and all those things. So this was a problem early on, but now our field is so big. So when you submit a paper, the papers are reviewed by the researchers in the same area. So nowadays you don't see comments like talk about convergence and all those things. So if one reviewer is asking that question, that means he doesn't like the authors. That is only that is the only thing you can say nowadays. If the person says, show the convergence proof for your metaheuristic algorithm, if the comment is like that, that means the reviewer doesn't want to accept your paper. It's not that he wants to see the convergence or anything like that. So, but on the other hand, when you ask for proofs for the convergence or whatever, it's in a way a little bit of contradictory, because metaheuristic methods were developed as an alternative for rigorous mathematical methods. So what it means is that metaheuristic methods are not expected to have all these rigorous proofs, because we ask only one thing. The basic requirement for metaheuristic methods, when I give you two solutions, are you able to say which one is better, which one is worse? That is the only thing we are asking. So that is the only thing we ask here. So with that, the proofs are very difficult anyway. So a little contradictory, as metaheuristics are developed to complement mathematical programming based methods, the mathematical methods. But still, there are some theoretical works. I am listing them towards the end of it. But the one observation I can share you now is that when researchers try to apply mathematical theories to swarm and evolutionary algorithms, they make lots of simplifying assumptions. So that again goes against the starting point. Can we have an algorithm without assumptions and restrictions? So when you want to do mathematical proofs, it comes to that point immediately. Then they will have lots of restrictions. So sometimes they work with single point. But all swarm and evolutionary algorithms are population based, or they use very small population. Sometimes they make some of the parameters, algorithmic parameters, constant. But most of the algorithmic parameters in swarm and evolutionary algorithms are stochastic. They are all randomized. So if you want to do analysis, then people do all these assumptions and restrictions and do some analysis. So those analyses are usually not useful. So if an analysis paper comes to me with lots of mathematical proof and derivation, the easy way for me to review such paper, because the paper may have 5-6 pages of mathematical proofs, and I wouldn't have time to look at all of them. So my easy query to the authors: so you have developed all these nice theories. Can you include any of these? Include your theories in any of the state-of-the-art swarm or evolutionary algorithm, and can you show me that the performance is improving due to your mathematical analysis? So almost always no one would be able to do that. So the authors they won't come back, they won't resubmit anyway. So, but anyway, some people are still looking at this theoretical analysis. So there are some negative papers. So I am also highlighting one particular paper. I think this particular paper is targeting an algorithm called harmony search algorithm. They just show harmony search algorithm is same as evolution strategy, and the evolution strategy is coming from 1962 or 63. So the method in 1962-63 is coming out as harmony search algorithm, but you cannot say they are the author is plagiarizing, because all these swarm and evolutionary algorithms, they have a story to write about. I look at this particular natural phenomena and I model this by this observation, and I come up with this equation. The problem is when you write down the equations they will be becoming very similar to some of the previously published methods. So that is where the problem is. So you can come up with lots of stories to motivate your particular new algorithm, but when you write the equations, they are going to be very similar to the previous ones. So that is the problem they highlight here. And this particular paragraph I copied from this particular paper anyway. So you can see, I think here the musicians playing together, flow of water. So it seems, so this is what I was mentioning, it seems that no idea is too far-fetched to serve as inspiration to launch yet another metaheuristic. So that is what I mentioned. If you want to become father of a method, then you listen to this. Any particular phenomena observation is not far-fetched to serve as inspiration to come up with another metaheuristic algorithm. See? Yeah, that's why you will see it in the next few slides. Yeah, that's right. So you see, you already started thinking about it. So my talk has an influence, I can see it. So someone has already started thinking along the lines. See, so here you have some of the names. So, but this, I must tell you, this list is not exhaustive. Here I am showing you about 20-30% of the names. So there may be about 2-3 times more names sitting outside. So since people are running out of names, they are giving citizenship to the species as well. Like you have a vulture optimization algorithm, then someone says Egyptian vulture. So if you know about Indian vulture or Chinese vulture, then Chinese vulture optimization algorithms. So it seems they carry passport also, I think. So you have some of these names here, but I think this listing excludes 2 older ones, like the evolution strategies coming from 1960s, genetic algorithms coming from 1970s, and then after that you have all others. And I think up to this point, I would say things were reasonably different. Before 95, the nature-inspired algorithms were fairly different. You cannot see the similarities, like the ant colony, particle swarm, and so on. They are fairly different. But after that, you would be able to relate one with another, the ones coming later. You can relate them when you look at the equations. the dynamics and equations, you will be able to relate many of them. So here you have all these things. So this is one way of looking at them, and this is another one. Differential evolution, it comes under more like evolution, but as I mentioned to you, the swarm algorithms are a lot more than evolutionary types. Evolutionary types are much lesser, I think. Swarm types are just far too many. Maybe when you look at these species, they are apparently different. Like you have monkey, donkey, pig, cat, dogs, they are different. But if you go to the genetic level, maybe the operations are fairly similar. So you don't have much choices there, I think, to come up with different evolutionary type algorithms, because the crossover, mutation, all those things are pretty much the same for many of them, I think. But looking at the appearance, you can differentiate them and come up with moth, flame, firefly, infinite number of names. So this is some more. And then, so it's never possible, because at this point in time, someone may be writing a new one anyway. So, and at one point, myself, I discussed with Dr. Das to see whether we can write a comparative study with these methods, but it's very difficult. When you have hundreds of them, comparing about 50 to 100 methods with another 50 to 100 is very difficult to compare them anyway. So it's far too many to compare. So for our policy for the journal is that when someone comes up with a new name, we immediately ask them, compare with best versions of one of the older methods, compare with the best one. If you can beat the best variant, like the differential evolution, it was published in 95, something like this. Differential evolution, actually it should be 95. But it has been investigated a lot, and there are so many improved variants. So if when someone submits a new metaheuristic to our journal, we ask them, you go and compare with the best version of differential evolution. It's the one published now recently. Don't compare with the 1995 version and then say our new metaheuristic is better than the 95 version. So by saying that, we reject all the new names coming to our journal anyway. But then there are lots of conferences and lots of paid journals. They need submissions. So there is always ways to publish all these new names. There are so many journals and conferences anyway. So these are the, I want to tell you a couple of names. So I mentioned these two researchers because together they have about 10 plus names under their belt. So this person has about 10 names, and this person has about 10 names, I think, the new names. So if you go to their home pages, you can see all the new names. Moth flame and krill herd, cuttlefish optimization, whale optimization, then someone said killer whale, and someone said white whale or something. So I don't know, so many names anyway. So there are also like monkey optimization. You have a monkey optimization, then another one puts spider monkey, another one says Aegis monkey or something. So Egyptian vulture, and also, and the fireworks, I don't know whether you call this nature inspired. Is it a nature inspired fireworks? Is it inspired by nature or human? I am not too sure. So the genetic algorithms. So I will briefly mention about genetic algorithms. How many of you are familiar with this genetic algorithms? Because even now, our field is known as genetic algorithms for many researchers from outside our area. Outside our area, everyone looks at them as genetic algorithms. Somehow the GA name is very popular. So I will briefly mention a little bit about genetic algorithms. So genetic algorithms are still competitive, good method, under only one situation. Your decision variables are just 0 and 1. If your decision variables are like on, off, yes, no type of thing, then you should really look at a good genetic algorithm, the binary version. But if your decision variables are floating point values like real numbers or even integers, then my suggestion is GA won't be very good. You can convert the floating point numbers to binary strings by quantization and all those things, but the method won't be effective. So if your problem is naturally a 0-1 problem, then genetic algorithms are good. But if your problem is 0-1 with permutation and things like that, then with genetic algorithm you may need some local search operators, local search heuristics. Some heuristics should be included if your problem is combinatorial or permutation type. So this genetic algorithms comes from early 1970s, I think 72 or 71. So the name was developed or created by John Holland and his PhD student. Together they came up with this name. I think John Holland passed away only recently, I think just 3 years ago, that's right. So he has done a lot of work, complex systems and all those things, John Holland. So you can look at this from 2 point of views, whether you want to simulate biological system or you want to solve real world problems using evolution. Our objective is to just solve real world problems using these evolutionary operators. So you have some biological terminologies. So the biological terminologies are not commonly used when you solve real world problems. When you solve real world problems, these words are more important. Offspring is a new solution. You generate a new solution. Then you have parents, recombination or crossover. You have recombination operators or crossover operators for binary string. You also have them for real variables. If your decision variables are integer type, you may have to include some rounding as well, ceiling or floor or something like that you have to include. If you use real parameter evolutionary algorithms. Mutation is a biological term, it's commonly used. Fitness, I mentioned to you a few times, it's a quality of your solution. Higher fitness means your solution is of good quality or better quality. And evolution is based on survival of the fittest realized by the selection operator. So the natural selection, you may have heard about as well, Darwin's theory as well coming from. So the survival of the fittest, it's not directly applicable for swarm algorithms anyway, but these are evolutionary terminologies. So the basic genetic algorithm or simple genetic algorithm is something like this. All our swarm and evolutionary algorithms, all of them, they work with a population of candidate solutions. So we work with the population of candidate solutions, and most of the time the population of solutions are randomly generated within the search space. So you usually have a bounded search space. Within the search space you generate the population of solutions mostly randomly. So the population is known as the potential solutions to your problem. Calculate the objective value of each solution. Chromosome, you can replace it by a potential solution. So for every potential solution, evaluate the fitness value. This is, for example, for your initial population. For example, as soon as you randomly initialize the population, you have to evaluate the fitness values. Then you go through the iterative process. This is what we call this as the generation, evolving through generations. So your population is going to evolve through generation. Evolution is valid for genetic algorithms. Select pairs of parents. So usually we work with 2 parents, but As you can see, for every step, researchers propose alternatives. So there are 3-way crossover, 4-way crossover, people propose all those variations. So you select 2 parents, and the 2 parents are going to generate offspring for you, children, and the common one is 2 children. 2 parents will produce 2 children, usually through crossover and mutation. So when you complete this process for the whole parents, the whole parent population, you have pretty much done 1 generation of work. Okay. The new offspring, they have to go through fitness evaluation. So you are going to evaluate the fitness of your new solutions, your offspring or children. So when you have the parents and offspring population, most of the time parent population and offspring population are usually equal in size most of the time. You have to combine them together, and for the next generation you have to perform some selection. You cannot keep on doubling the population through the evolution, so usually we keep the population size fixed. So if you have 100 parents, they generate 100 offsprings, your population will become 200. After the 200 you have to do some selection to keep only 100 as parents for the next generation. Okay. So there are many choices for this selection as well. Different algorithms use different methods to do this selection. So usually the stopping condition is whether a good quality solution is found or you have exhausted the given computational budget or computational time.
So when do you know it's good enough?
Some objective functions can give you some indications, like some of your objective functions may have a global solution as 0 if you are error minimization and things like that. So some error minimization problems have 0 as the global solution. So then you know you are close to it, but it may not be the case always. So you need to have some problem knowledge also.
So you get the upper bound for the or lower bound for the problem to work on?
Upper bounds and lower bounds are usually for the decision variables in the real space.
Talk about the objective values that you know what the range that you get. You can estimate about the bound for the optimal solution.
I mean, when you want to do the estimation by evaluations, you are making use of your resources anyway. So we don't usually, I mean, in the evolutionary computation field, we don't explicitly search for the bounds anyway, but this statistics can be accumulated over the generation. As you evolve, we usually keep these values, because some of these values can be used for your evolution. Like in the multi-objective, sometimes you may have to normalize the objective values. So in the multi-objective case, one objective may be 0 to 1, another objective may be 0 to 1000. So you may not be able to combine them or compare them. So you may need to do some normalization. So these statistics are usually, if you cannot deduce immediately from your objective functions, if you are unable to deduce them from your objective functions, then you may collect these statistics during the evolution and make use of them. But sometimes the objective function can tell you something, or you have some problem knowledge to see which one is a good solution, acceptable solution for your problem. So if you are solving a problem, you should have some idea what is a good solution, is that right? So some idea should be there anyway. And also when you look at the evolution, the evolutionary process may be generating hundreds and thousands of solutions anyway. So when you go through this process also, you will get some idea. These are the solutions I am encountering all this time, and this is what I am getting now. So
basically you can see the loss function or objective function, the difference between 2 iterates, and see if they're small enough, you think they're converged or something.
It can converge to a local solution as well.
but sometimes, is it local solution good enough? Or like
that is the person with the problem has to say, I think. Yeah. So I mean, the metaheuristic algorithms are not promising you of the global solution. Yeah, they try to give you a good solution within shorter time, like I think. Yeah. And the problem quality should be assessed by the owner of the problem, I think. So as I mentioned to you, the original GA, the GA before 1990 or maybe 1985. Before 1985, the GA was just binary based, 0-1 representation only. After 1985, researchers developed real parameter genetic algorithm or real coded genetic algorithms. In my opinion, real coded genetic algorithms are not very competitive as differential evolution, for example. So if you are looking at the real parameter, real variable optimization, differential evolution is a good candidate to look at. Real variable optimization. And if you are looking at 0-1 solution representation, on, off, yes, no type of problems, then genetic algorithms, the binary genetic algorithm is still a good competitive candidate to look at. So although real coded GAs exist now, but before 1985 it has been always 0-1 for genetic algorithms. So test means evaluate a particular solution string to find a score. Score you can say as a fitness value, quality of the solution. So as I mentioned to you, GA is still a competitive method if the problem naturally has a binary solution, 0-1 solution. So each decision variable is either 0 or 1. Each decision variable 0-1. But don't convert integers to binary strings. Say if your solution has 5, 6, 7, 8, 9 values, these numbers, integer numbers, don't convert them to binary strings, then it won't perform well. You will have other methods, DE and other things. So it is possible to encode integers, floating values with quantization within the pre-specified ranges and so on. But as I told you, this is not a good approach. So don't use this approach. So this is about the search space or fitness landscape. So where do you think the evolutionary algorithms, swarm algorithms can work? Swarm algorithms, evolutionary algorithms, they can work on these two spaces. So this space is maybe not so smooth, little bit discontinuous, is that right? So for this space is okay for evolutionary algorithms. We are not doing any differentiation or anything like this. So this discontinuous space is fine. This space is also fine for swarm evolutionary algorithms, but this one is not good. Swarm evolutionary algorithms, they make use of some sort of continuity in the quality of solution. So if you reach here, then you may be able to make some movements this way to go to the peak if you are maximizing that function. But if you look at this, there is no structure in this problem. So if you apply evolutionary swarm algorithms here, you are not going to find anything useful here. You may not be able to find the solution. But then if you have a error surface like this, then no solution is good as well. Because if you get any solution, all these solutions are not so robust. The robustness means if you just deviate little bit from the solution, your objective value goes away anyway. So it's not a stable objective function as well. So parent selection, crossover, mutation operations. For genetic algorithms, you need these three operators: parent selection, crossover, mutation. For the parent selection, usually the method is roulette wheel, but there are so many other methods. As I told you, researchers, these are heuristics or metaheuristic algorithms. So for every operation, people can come up with different heuristics. So there are lots of heuristics for each operator, each step, and so on. The roulette wheel is more like a fitness proportional selection. So the selection is you are looking for parents to generate next generation offspring. You are looking for parents to generate offsprings. And how do you select parents? Usually you do fitness proportional. That means if a particular solution has high fitness, that means the quality of the solution is good. It is going to have higher probability of being selected as one of the parents. So you usually do fitness proportional selection, and you select two parents, and then you do crossover followed by mutation. Mutation is just flipping a few bits, maybe a couple of bits or 1 bit, for example, and it is also done randomly as well. So this is a simple crossover operation. This is known as the single point crossover. You select two parents. The two parents are selected based on their fitness proportional selection, and then you randomly select 1 point to do the 1 point crossover, and then you can have the two offsprings. So this is a simple crossover, 1 point. As I mentioned to you, you can have 2 point crossover, you can have multi-parents crossover, you don't need to have just two parents, you can have multiple parents. So all these things are possible. And also uniform crossover. Uniform crossover will allow you to mix the bits more freely. Like offspring 1 can select the first bit from the first parent, second bit can come from the second parent, third one can come from the first one, and so on. That is uniform. It's all done randomly. For example, this crossover point is randomly selected, stochastically selected, and then when you do the uniform crossover, whether you want to take from parent 1 or parent 2, that can be randomized as well. It's all randomized. And the mutation is usually 1 bit position is flipped most of the time, and that the position that you want to flip, that is also randomly selected, and then you flip. 0 goes to 1, 1 goes to 0. So GA, as you can see, it was introduced in 1970 something, 71, 72. There are lots of variations. Parent selection variation, you have this kind of things included as well nowadays. Mutation for non-binary encoding is also there, so you have lots of variations. So my suggestion, if your problem is real variable, your problem has real decision variables, then differential evolution is a good choice to look at. If your problem is naturally 0, 1 without permutation or combinatorial type, then the genetic algorithm is still a good one to look at. Differential evolution, particle swarm, all of them have been done for binaries also. They do some sort of thresholding like. But GA is still a good candidate. But if your problem is combinatorial type, then you can choose almost any one of these swarm and evolutionary algorithms, and then you hybridize with local search methods. Because for combinatorial or permutation problems, the swarm and evolutionary algorithms are not really doing the fine search. They are only maintaining population diversity. The swarm and evolutionary algorithms, they maintain the population diversity, where the local search heuristics are doing the real trick, improving your fitness values. So when you hybridize them, they work very well. Most of the recent papers from permutation combinatorial problems are this nature. The swarm evolutionary algorithms hybridized with local search heuristics, problem domain based. So I am not doing much of combinatorial works. One reason is again the citation based analysis. So if you look at the permutation combinatorial problems, each problem is investigated separately, like TSP is investigated separately, job shop scheduling, flow shop scheduling. Each one of these problem is investigated as a separate problem. So when you publish a paper in TSP, most of the other combinatorial permutation researchers won't look at them. I think it's only the TSP people are looking at it. So the communities for each of these combinatorial cases are smaller, but in real life, these permutation combinatorial problems are found in real life. So if you are going to solve real world problems, then these are the major ones as well. But when you look at the real coded optimization problems, when you come up with a real parameter algorithm, you can solve real variable optimization problem from any field, power engineering, antenna, signal processing, microwave. So we have applied our algorithms in all these areas, optics. Anywhere you find a real coded real variable optimization problem, you can apply the differential evolution particle swarm. So you have a much wider space with one algorithm development. You develop one algorithm and put it through all of them in the same way. Not much modification needed here. So maybe with this we stop for the break. I am 5 minutes late as well.